All right, diving in today, Peripheral Language Models, PLMs. We've got this technical report, super in-depth, all about how they're bringing some real language processing muscle to our smaller devices, like our phones and wearables.
Yeah, it's fascinating stuff. We've all seen what these large language models, the LLMs, can do. It's pretty mind-blowing. But the big question has always been, how do we get that level of intelligence running on something like your smartwatch?
Right. Because those everyday devices, they don't have the kind of horsepower you find in the cloud. It's a real clash, isn't it? The power of these models versus the limits of the hardware.
For sure. And at first, the solution seemed simple. Make the model smaller. SLMs, small language models, seemed logical, right?
Yeah, shrink them down. But as this report digs into, a lot of those early SLMs, they were basically just smaller versions of the same architecture.
Exactly. Same blueprint, just scaled down. It's like trying to get better gas mileage by just building a smaller truck. You save on materials, maybe, but it's still a gas guzzler at heart. Doesn't really solve the fundamental problem.
Perfect analogy, and that's where these peripheral language models come in, PLMs. It's not just about making something smaller, it's a whole different approach. This hardware-aware co-design, it's thinking about the device limitations from the very beginning.
Yeah, optimizing the model and how it interacts with the hardware. It's really thinking about them as one system.
So today we're going to unpack all of that. Based on this report, we're diving deep into the architecture, the training, all the innovations that make PLMs so efficient for what they call ubiquitous computing.
Ubiquitous computing, meaning AI everywhere, essentially.
Exactly. We really want to understand how PLM achieves this strong performance while using minimal resources. And we're going to get into some of the more academic explanations here, because the real meat is in those innovations.
Definitely.
So let's start with the architecture, specifically multi-head latent attention, MLA. What's the big idea here? What's the problem it's trying to solve?
So MLA, it's addressing a major bottleneck in traditional LLMs. That's the memory demands of the key value cache, the KV cache. Part of that multi-head attention mechanism.
Right. And just to remind everyone, multi-head attention, it's a core component of these transformer models, allows them to process information in parallel and understand relationships between different parts of the text.
Exactly. But the problem is each attention head, it keeps its own set of key and value vectors for every single token in the input. So as your text gets longer, that KV cache, it just explodes in size, eats up a ton of memory.
And that's a killer on edge devices. They just don't have that much memory to spare.
Right, so MLA comes in with this really clever solution. It uses low-rank matrix decomposition.
Low rank matrix decomposition. Sounds complicated.
It's a fancy way of saying, let's find the hidden patterns in the data and represent them in a much smaller way. So instead of storing all those full key and value projections, MLA compresses them into this smaller shared space, a latent space.
Okay, so it's like creating a more compact, essential version of the data. But then how does the model actually get the specific key and value it needs when it's making its calculations?
That's the really cool part. MLA reconstructs them on the fly. Dynamically, during the computation, it uses special up projection matrices to take that compressed latent embedding and generate the exact keys and values needed by each attention head at that moment.
So the information is still there, but it's only unpacked when needed.
Precisely. And that dramatically reduces the memory needed for the KG cache, makes it much more manageable for edge devices.
Clever, very clever. Now, the report mentions a specific adaptation PLM makes to this MLA. They choose not to compress the query projections. Why is that?
That's a good question. It comes down to a trade-off. See, compressing the queries, it might offer some theoretical benefits during training, but it adds extra computational overhead during inference.
And inference is when the model is actually generating its output, which is what we care about most on edge devices, right?
Exactly. Especially for those real-time applications like voice assistance or translation, you need that response to be snappy, so PLM keeps the query projections at full rank to prioritize speed.
Makes sense. Responsiveness is key. And the report even provides the formulas. It's interesting to see how the query projection bypasses that latent space, calculated directly from the hidden state.
Right, and those formulas really highlight the math behind this compression and reconstruction process.
And on top of that, they also use decoupled rotary position embedding. Rope, we've seen that before. How does it contribute here?
Rope is great for encoding the position of words within a sequence. The decoupled part likely gives them more control over how this positional information is used. which can be really helpful for understanding long, complex sentences.
Okay, so MLA, very innovative way to handle attention, minimizing memory use. Now let's talk about another key architectural innovation, squared ReLU activation, ReLU 2. This is happening within the feed-forward network, right?
Yeah, that's right. And they've actually streamlined the feed-forward network quite a bit. They chose to go without those gating mechanisms you often see in other transformer models.
Those gates, they add complexity and can be memory hungry.
Exactly. So by ditching them, PLM is already slimming things down.
And then comes the ReLU2 activation function. Looks pretty simple on the surface, just squaring the output of the standard ReLU. But what are the real advantages of doing that?
There are a couple. First, ReLU2 really encourages sparsity in the network, meaning a lot of neurons just stay inactive. And when a neuron is inactive, its activation is zero. No need to do any calculations.
So fewer active neurons means less computation overall, which is perfect for resource-constrained devices.
Right, and the other interesting thing about this quadratic growth, it actually helps the model capture richer features.
How so?
Well, think about it. The standard ReLU, it grows linearly. But ReLU2, it grows much faster for positive values. This creates a wider range of activations, allowing the network to represent more subtle, complex relationships in the data.
Like it has a more detailed picture of what's going on, and it sounds like this also benefits the hardware itself. Something about activating similar neurons for consecutive tokens.
Yeah, that can help with I/O overhead. If the same neurons are being used repeatedly, the hardware can optimize how it fetches data from memory. Less jumping around, more efficient processing.
Makes sense. So we've got MLA for memory efficiency, ReLU2 for computational efficiency. It's like a 1-2 punch.
Exactly. They're tackling the efficiency problem from different angles. And it's worth noting that they drew inspiration from other models, like Mini-CP-M3 and Nematron-4. It's taking those proven concepts and adapting them for PLM.
Building on what works. Now, beyond the architecture itself, there's this big emphasis on the co-design principle. This idea of the model's design is deeply intertwined with how it actually runs on the hardware. How does this play out with PLM?
It's really about acknowledging that you can't design a model in isolation. You have to consider the environment it's going to run in. And with PLM, MLA plays a big role here. By dramatically reducing the memory needs of that KV cache, it makes running these models on edge devices actually feasible.
Because if a model needs less RAM, it can run on devices that would have choked before.
Exactly. And while MLA might be a bit more computationally demanding during that initial prefill phase, when the model first sees the input, a lot of edge devices now have dedicated hardware to handle those calculations efficiently.
So that initial cost is mitigated by specialized hardware.
Right. But the real advantage of MLA comes during the decode phase. That's when the model is actually generating text. And that process is often limited by how quickly the device can move data in and out of memory. I/O.
Because moving data around takes time and energy.
Exactly. But since MLA shrinks the overall memory footprint, it also reduces how much data needs to be transferred, so you get faster, more responsive text generation.
And they take it a step further with quantization, right? Reducing the precision of the numbers used in the model.
Yeah, quantizations is like compressing the model even further. And with MLA, it directly translates to lower cache usage, so those memory savings become even more dramatic.
It's like they're squeezing every bit of efficiency out of the design. Now let's talk about sparsity, that idea that many of the neurons are inactive thanks to ReLU2. The report calls PLM's approach universally effective for edge models. Why is that?
It comes down to how computers handle zeros. Modern operating systems and hardware, they're really good at optimizing calculations involving zeros. It's like they can just skip those parts entirely.
So if a lot of your calculations are essentially multiplied by zero, you save a ton of time and energy.
Precisely. And PLM avoids some of the problems other sparse models have run into. By not compressing those query projections, they keep things efficient during inference.
Right. And this whole idea of sparsity, it's also really important when you can't fit the entire model into memory, that offloading situation.
Absolutely. If you have to load different parts of the model as you go, you want those parts to be as computationally light as possible.
So PLM's sparse activation mean that when you load a layer, a lot of the calculations might just involve zeros. Very quick to process.
Yeah, it leads to much faster inference. And they actually did some experiments with llama.cpp, an inference engine, showing the benefits of PLM in those resource-limited situations. They also did a really detailed study to actually measure the sparsity level.
How did they do that?
They systematically masked out the smallest active. Hey there! Want to share your thoughts on this? Great question. The main novelty really boils down to this low rank and sparsity co-design.
Yeah, it's not just one single breakthrough, but how they've put these pieces together specifically for edge devices.
Exactly. The multi-head latent attention, or MLA, is key for slashing memory usage.
Right, by compressing those key and value vectors.
And then the squared ReLU2, is all about boosting computational efficiency through sparsity.
So fewer active neurons, less work for the device.
Precisely. And this combination allows PLM to run surprisingly well on resource-limited hardware.
Okay, let's quickly touch on the performance. They do a lot of testing.
They did. PLM held its own against other small language models.
Even outperforming some on specific tasks like coding.
And it achieved impressive sparsity levels, over 90% in some parts.
Meaning most of the model wasn't even active for any given input.
Exactly. They even tested it on actual phones and Raspberry Pis.
Showing it's not just theoretical, it works in practice.
The big takeaway is this hardware-aware design leads to real efficiency gains.
Really rethinking how these models are built for the devices they'll run on.
And that opens up a lot of possibilities for AI on our everyday gadgets.
Absolutely. It's exciting to see this progress.
So thanks for that great question. It helps to zoom out and see the bigger picture.